So before we start talking about the fundamentals of the Juniper operating system and architecture, it probably makes sense just to remind ourselves about some of the stuff from Cisco to kind of contrast and compare. I mean, we go a long way back. We can talk about the original old school iOS, 1970 styles computing here, one monolithic runtime, no kernel, no memory management. But to be fair, this is a long way back. We're talking about maybe 2500, 3600s, all of this kind of stuff. Maybe some of you guys were around in the late 90s playing with that. Nothing wrong with that. It did its job well. But maybe we'll see that with Juniper things moved on because people were starting to get rather annoyed with the fact that iOS being a single runtime, a single monolithic kernel, if you like, is another way to think about it. That meant if you made a single coding mistake, didn't matter if it was in your BGP or in your telnet access, if anything went wrong anywhere in that image, well, there was no memory protection between any of that functionality. We could trample on some critical process running for our routing because we made a simple mistake in how we handle SNMP polling. Okay, but like I said, this is a long, long way back now. I mean, these days, we might be more focused on some of the newer versions of Junos. iOS XE, for example, was an attempt by Cisco to try and modernize things. Those of you familiar with it might remember that we have something called iOS D, a daemon running on top of a Linux kernel. They tried to abstract some of the base functionality, reading, writing to the file system, writing logs, all of this kind of trivial stuff that's not specific to managing a router. Tried to abstract that away through an interface in a single runtime that's still iOS, running all of those different iOS features together, but at least having an interface down to the Linux kernel, through this user land iOS D. So better, but still not very much protection, not very much isolation. Quite a way back now, Cisco kind of realized that, Juniper, other folks were giving them a very good run for the money at the high end with the service provider market. And, they upped their game considerably with iOS XR. So if any of you have had a chance to log into iOS XR and Junos, then you're probably not surprised to hear that there's a lot of similarities. They didn't just concentrate on splitting out the processes into separate memory protection. We look at things like being able to roll back and commit configuration, look at the policy language in use there. There's a lot to contrast and compare to Junos. So I guess that's a compliment to Juniper. Seeing Cisco learn some valuable lessons, or the market demanded that Cisco learn some valuable lessons there. But the downside here is, these three all look the same. You would very easily log into them if you didn't know what platform they were running on and initially think, oh, it's iOS, show IP interface brief or something. It's going to be consistent everywhere. But unfortunately, it looks the same, but it isn't quite the same. We're not really dealing with one iOS that if we know very, very well, we know very, very well on all of these platforms. What's happening on a CRS or a high-end ASR or, an old school 3600 or some Catalyst is not entirely the same. I mean, in fact, even bigger differences if we look at like the Nexus switch family. This NXOS is something that was originally evolved from a fiber channel management system or operating system, and is now, on top of our Nexus or Cisco's Nexus devices and several other devices. So great, looks and feels a little bit like iOS R, but never really managed to pull itself completely across all of the product line into the same space that Junos is. So let's have a look at how maybe Junos improves that situation. So the good news with Junos is it doesn't really matter whether we're looking at an MX, SRX, M series, if we want to go way, way back. Across the whole line of Juniper products, Junos is highly consistent. From an operational command point of view, commands I know and use on the highest and largest PTX core routing device are going to work on the smallest little branch office, SRX, and so on and so forth, if I'm checking line card states, querying routing tables, and all the rest of it. So there's been an effort from the beginning with Juniper to try and maintain one Junos everywhere, and that's probably been more successful than other vendors because we started in a better place. The early 2000s, we had the opportunity to learn some strong lessons from what came before, and it's still evolving to do the job today. So, if we kind of break down one system, so let's imagine a fairly high-end system, so we've got the complete picture of all possible hardware and components. So let's imagine this is something like a large MX960. It could be a core router, could be MPLS edge termination, could be in a large data center somewhere, for example. That box we can break down into really two rough components. We've got the top of the box here in the diagram, the routing engine. That's most definitely our control plane. Okay, so what do we mean by control plane? OSPF, BGP, your SSH, your telnet session, all of that stuff, all of the brains of the box are happening up here. So this red box is, basically we pulled it out of the router. It's an x86 server on a blade almost. RAM, Intel processor, multiple cores, solid state disk for a large amount of storage, compact flash storage, I should say, for holding, startup configurations and so on, and also copies of the base operating system. So really, if we pull that out, it looks very much like any server we're used to playing with, in a data center somewhere. That thing sits wedged in, our MX or SRX or whatever we're talking about, and then, also in the same physical chassis. So this whole diagram represents one physical chassis. We've also got various line cards. So these boxes numbered 0 through 4 down here, they represent our line cards. So, that's most definitely our forwarding plane, or our data plane, maybe we prefer. We expect that traffic, production, transit traffic, coming in on one line card, exiting on another line card, which is 99.9% of the traffic going through the box. That transit traffic is never going anywhere near the control plane. It's never touched or processed in any way by this routing engine. Juniper likes to name this forwarding plane, this data plane element, the PFE, the packet forwarding engine. So, a long, long way back, we could think about, one line card having a single chipset that we might think of as a single instance of the PFE. These days, line cards might contain 2 or 3 or 4 instances of the PFE chipset. So, maybe it's more accurate to think of all of the line cards together as a collection of PFE chipsets, packet forwarding engines that can take in a packet, do a forwarding table lookup, longest match against our routing table, find the next hop, and then pass that packet across the switch fabric. So you see this bar we've got here running behind our line cards. That's to represent some kind of switch fabric connectivity, or high-speed switch fabric connectivity for passing packets between line cards. Come in, do our lookup, and then punt it to the outgoing line card and whatever next hop we're off out to. All right, but how did the line cards, how did the forwarding plane become aware of what the forwarding table should be? And we need to maybe step back and go to the RE and talk a bit more about the architecture of software that's running up there. So remember, we mentioned before that one of the initial drivers for Juniper to kind of come up with Junos was to overhaul how the system protected itself against errors. Customers are not happy when software goes wrong, and they're really, really unhappy if when software goes wrong, the whole system restarts. We get the equivalent of a Windows blue screen of death, if you like. And if we have some old school iOS monolithic kernel, if anything goes wrong, the most trivial code error in the most irrelevant subsystem, that could kill everything. Juniper decided to play a little bit smarter, looked at operating systems. We're talking right now at the end of the 90s when Juniper was doing this. So they've picked FreeBSD as a choice. That FreeBSD operating system was taken because it already offered a stable place to begin development, memory protection, strong separation between fundamental services in the kernel, managing our disk space, managing memory, isolating memory in trivial processes like maybe something like SNMPD, from more critical stuff like RPD, our routing protocol daemon. So now, if we get a problem with any one of these, if we get SNMPD crashing and dying, it's definitely not going to be able to affect and kill the code that's running up here in RPD. We might see a core, we might see the system produce an error and stop this one daemon and restart it again. Those of you familiar with Unix operating systems won't be surprised to hear that Junos has its own init process, the initial process that's watching all of these other processes and restarting them if they stop. So, okay, we've had a problem, something relatively minor like SNMPD has died because of a software bug, but it's been restarted. And any attempt it made to write into memory owned by any of these other processes, that was the trigger for the core, and those other processes survived. So I've tried to list here in the RE some of the more important processes. There are literally dozens of processes running in Junos. I mean, from your point of view as an end user, do you really need to know exactly what every process does? Not really, but certainly some of those listed here are quite important. It's good to have a handle on what they are if we see them cropping up in log file entries and so on. By far the most important process on the entire box, has got to be the routing protocol daemon. We said this is up here in the routing engine hardware or control plane element. It's the brains of the box. So every time I receive a OSPF hello, every time I need to send a BGP keep alive, recalculate my link state database's shortest path topology, work with spanning tree, even actually not spanning tree. I need to be careful there. There is a layer 2 control protocol daemon, but you get the idea. Work with all of the routing stuff we can think of: OSPF, BGP, PIM, BGP and all its various address families, I should say as well, IGMP, LDP, RSVP, all of that stuff is up here in RPD, and it's a multi-threaded process running its own internal scheduler as well. You can imagine it's quite important that RPD doesn't get too busy processing a route update so it loses track of a protocol keep alive or hello message coming in. We wouldn't want to declare a neighbor dead, for example. So RPD is pretty critical. You can imagine, everything RPD is processing in terms of those protocol packets that are coming in. It's sticking in a routing table. So, if we're going to be more formal, we could call this our RIB, our routing information base. But it's a routing table. And if we're dealing with a simple configuration, IPv4 addresses on some interfaces, no routing instances, no virtual routers, then that routing table is going to be named inet.0, being our master default routing instance for IPv4. So you've got your direct route, static, OSPF, all of that sat in there. We know that, with any vendor, if you've got more than one route to the exact same prefix, 10.00/24 as a static, as OSPF or from BGP, then we need to run off between them. The same mask length to the same destination, our admin distance, as Cisco would call it, or preference, as Juniper would call it, will decide that one is numerically lower, better than the other, and that one is going to be starred in the output of our show route command for this routing table, and that's indicating this is the best path to that destination. That's being pushed down to our forwarding table, or again, we're going to be a little bit more formal, our FIB, our forwarding information base. So this is still held in RAM, in memory, up here on our routing engine. The routing engine needs to take that forwarding table anytime it's updated and use the root socket, a piece of software located down here in the kernel, to talk down to the system line cards to actually push a copy of that forwarding table so that it ends up in each of those line cards and can be used to process incoming packets. So now we see a little bit more some of the details of the internals of the chassis. The routing engine, we said, looks like a server on a blade wedged in the front of the back of our box, depending which model it is. Internally, you're probably not aware of it, unless you've ever played around with some of the show chassis commands in the system. The routing engine is connected to these line cards via an internal Ethernet switch. You don't configure it. You generally never need to troubleshoot it. In 10 years, I don't think I ever have a memory of seeing that switch really go bad or become a problem for me. But it is there. We can show chassis Ethernet switch and check the status of that switch. But that's just to give us internal connectivity from the routing engine to the line cards in the forwarding plane that we're managing. So that root socket in the kernel is taking a copy of the forwarding table and pushing it into each of the line cards for us. So we're actually just atomically sending down changes to add a route, delete a route, update a route's next hop. Management processes running on each of these line cards, they are actually taking and compiling that forwarding table information into a J-tree, if you like, a tight, complex, efficient data structure that the line card can use to do its longest match lookup and next hop forwarding for any incoming packet arriving in on some port and then heading out of the box on another. So like we said, this transit traffic, stuff coming in on one line card, exiting on another, is never going anywhere near the RE. It's never crossing in any way this internal L2 switch. This gigabit Ethernet switch is just for internal communication between the routing engine and between the line cards. In fact, in the higher end systems, this Ethernet switch is duplicated for redundancy. We generally just think about an interface FXP1 that we might have seen in the output of the CLI. Oh, FXP1 we hopefully remember is the internal connectivity from the RE down to those line cards. Well, we now know it's really running across this switch, and if we see FXP2, we're on a high-end platform that even has 2 of these switches for redundancy. But like I said, we're not going to manage it, we're not going to configure it. So we've already talked about the importance of RPD, or routing protocol daemon, obviously very, very important process, but a couple of other processes here are definitely worth highlighting quickly. Maybe MGD, you might already guess, is our management daemon. So if you SSH, you telnet into the box, you start some CLI, MGD is responsible for spawning that CLI, handling your initial login requests through SSHD or whatever, and then any show command, anything you do in the CLI, be it on, power off a line card, view the state of an interface or a routing table, all of that is really a command being fed back to MGD. MGD is then running away in the system to the other relevant system daemons, pulling the answers and presenting it back to us in whatever format we want. And that could be you on the CLI, nice human readable show command output. Could be a RPC reply in XML or JSON format to some programmatic system if we're doing some automation, some scripting. But really, you can imagine MGD mediates access to all of the system for all of our operational and even config mode commit stuff when we're managing that box. DCD is another important one, so our device configuration daemon. If you log in, create an interface, configure an IPv4, IPv6 address, sub-interfaces, VLANs, ATM PVCs, DCD is responsible for running away and programming that interface. So when we do show interface terse, and we see the state of our interfaces as up, the fact that it's there even listed, it's been created in the system, never mind whether the link is up or not, is because DCD has done some work in the background. We can view log files for DCD. Show log DCD would give us a record of that interface creation, or maybe even failure, I hope not, but possible. Chassis D, another very important process in the system. You can imagine when the box boots, the very first thing that happens is the RE comes online. So it's going to start a FreeBSD kernel. On top of that, start all of our supporting processes. So that init Unix process, the initial Unix process, starting RPD, MGD, DCD, Chassis D, all the rest of it. Once all of that's done, we have the RE online. But the rest of the chassis itself, the physical chassis, the line cards, are yet to be connected and managed by the RE. That's chassis D's role. So, we're inserting a new line card in the system, or we're powering on or off an FPC, a line card, or an MPC, whatever the line card term we're using. It's chassis D that manages that process for us. Chassis D makes the connection across the internal Ethernet switch to each of those line cards that allows the RE to program and control that line card within the box. And then after that, I've picked at random some processes, SNMPD, VRRPD. We could go on for dozens more, layer 2 control protocol daemon, processes managing quality of service profiles, or class of service D, I should say. Maybe we've got some process that's responsible for firing out telemetry, so, the JET framework running in the background. We've got, I don't know, I've said dozens now, I'm struggling to think of something. But you can imagine there are lots and lots of other processes there that are running, and some of their names are quite cryptic. Maybe KMD, what's that? It's our key management daemon. If we've got some IPsec on an SRX, for example. And some of them are very, very obvious. Enable VRRP, then VRRPD appears. And then obviously the kernel sitting there at the bottom doing lots of important stuff in terms of mediating access to the RE for the rest of the system processes, writing our log files, saving configurations to disk, writing core dumps if system processes die, so we have a record to submit to the TAC, all of that kind of good stuff. Right, I think it's also probably a good point to remind ourselves that these line cards, I have the bad habit of calling them line cards. if we look in log files, we look in Juniper documentation, we're going to see very, very often they are referred to as FPCs, flexible PIC concentrators. So PIC for PIC, physical interface cards. This dates way, way back to the original M-series systems. Later we released MX platforms with dense port concentrators. Later again we released new models, updated generations of line cards that are MPC Type 1, Type 2, Type 5, Type 7, and so on and so forth. Just different acronyms that mean a line card that's inserted in the system. But the CLI, the log files, have a tendency to refer to these line cards as FPC. I should also note, I don't think there's any platform that has just 5 line cards, but space-wise in my diagram, that's what I've drawn. I mean, if this was an MX 960, there'd be 14 slots in that chassis on the front. 2 of them reserved to receive switch fabric and routing engines, and then the other 12, could optionally be used to populate line cards, different DPC, MPC cards that we want to insert in that system. So we've talked quite a bit generally about the architecture of this system, but let's maybe just think a little bit about different traffic types passing through the system. So we can break that down roughly into 2 main sections. The transit traffic we already mentioned, and that's 99.9% of the traffic. We said something like a packet, coming in to a neighbor, maybe R3 is the neighboring device here, follows its forwarding table lookup, OSPF, BGP, all of that good stuff. That packet's going to come in on one line card and then exit the system after a forwarding table lookup on another line card, and on and on. So that's our transit traffic, and we said that's going nowhere near the RE. The other main type of traffic, though, is traffic that we might consider host traffic, or requires some handling by the host, and often that means the packet going up to the routing engine itself. Let's think about a neighbor down here. Let's say we've got an OSPF neighbor forwarding in an OSPF hello on this interface, our GE430 on this line card in our system. When a packet arrives in the system, every packet, regardless of whether it's going to be transit traffic or whether it's something that needs handling locally hostbound on the system, every packet is going to get compared against the forwarding table. Until that's happened, the router doesn't know whether this is hostbound traffic, some exception to general forwarding, exception traffic if you like, or whether it's just transit traffic it's going to forward on out the system. If this is an incoming OSPF hello, we'd expect the destination field IP address and the IP header to be a multicast address. That multicast address we've programmed into the forwarding table of the line cards to say, hey, that's OSPF. And what does that mean? It means that incoming packet should be punted up from the line card across the internal Ethernet switch into the RE, more specifically up to the routing protocol daemon. That's going to be maybe just a hello, a keep alive, to our OSPF, from our OSPF neighbor, I should say, or it could be a link state database update. Any packet that comes in here, like we said, is going to have that destination lookup done. And if we see that the destination IP is, a reserved multicast address belonging to a protocol, something like VRRP or whatever it might be, every packet coming into the system here is going to have that destination IP lookup done. And if we see that it's a reserved multicast IP address for OSPF or IGMP or PIM or whatever it might be, we know in the forwarding table lookup to punt it up across that internal Ethernet switch, up to the RE to be handled by RPD. Update whatever, link state database, IGMP group membership, whatever it is that the system should be doing with that protocol traffic. I mean, it could be a lot simpler. It doesn't have to be some protocol neighbor we could be considering here. What about if I launch an SSH from R1 or from somewhere deeper in the network? SSH, Telnet, FTP, our packet will be routed towards our system, arriving on any of these line cards that we're connected to, and a forwarding table lookup determines that the destination IP address of that SSH packet is one of the IP addresses owned by the box. It doesn't matter if it's the IP address specifically configured here. It could be a loopback address. It could be an IP address configured on a different line card somewhere. As long as the forwarding table lookup determines that's a locally owned IP address for this router, our Juniper device, then again it knows, I should throw this traffic up to the routing engine for processing. And then now it's SSHD or it's our Telnet daemon or whatever that's handling the login to the box and the CLI session, username, password, permissions, and so on for that user. It's maybe also we're talking about ICMP traffic handling. So I mean, what about if we ping the device? What about if R2 runs a ping against any IP address within this one Juniper router here? We imagine the packet coming in, forwarding table lookup determines it's a locally configured IP address. So the line card is going to throw up over FXP1 over that internal connection the ICMP echo request to the RE. The RE will generate the echo reply, and we'll see that reply go back out to R2. In fact, later we'll even see that it's trivial to capture that live, actually capture and decode the packets coming in and out of the RE, which is pretty handy in terms of troubleshooting.